The discovery of supersolid light, a new frontier in physics. In an unprecedented breakthrough, a team of Italian scientists has demonstrated that light can exhibit properties akin to what we would call a supersolid, a rare and exotic state of matter. This revelation, published in the prestigious Nature journal on March 5th, 2025, heralds a transformative shift in our understanding of the fundamental behavior of light. Traditionally, supersolidity had been observed only in extremely cold atomic gases. The ability to induce supersolid like behavior in light opens new avenues for exploring the interaction of light and matter, with significant implications for both theoretical physics and practical applications. This video is going to go into the concept of supersolidity, the specifics of the experiment that led to the discovery, and the broader implications, the challenges ahead, and the potential directions for research in the future. So let's understand supersolidity. Supersolids are a paradoxical state of matter where materials exhibit both solid and superfluid characteristics. Superfluidity is a quantum mechanical phenomenon where a fluid can flow without viscosity, encountering no resistance. A supersolid, therefore, flows like a liquid but retains a rigid, ordered structure that's typical of a solid. This duality arises from the unique arrangements and interactions of particles at the quantum level. Let's go into the historical context of supersolidity. The concept of supersolidity was first proposed theoretically in the 1950s. Physicists speculated that under extreme conditions, matter could exhibit this unique duality. The early theories suggested that solid helium, when cooled to near absolute zero, could form a supersolid state. However, the phenomenon remained elusive for several decades due to the limitations of technology at that time. It wasn't until the early 2000s that scientists observed hints of supersolid behavior in ultra cold helium experiments. Researchers noticed anomalies in the rotational behavior of solid helium, suggesting the presence of a frictionless component. However, these findings were later challenged and debates ensued regarding the true nature of what these observations meant. More recent advancements have led to the creation of supersolid states in Bose-Einstein condensates, BECs, which were composed of ultra-cold atomic gases. These experiments provided crucial insights into quantum mechanics and set the stage for future and further explorations into the exotic behaviors of matter under extreme conditions. Let's talk about the characteristics of supersolids. Supersolids are distinguished by their coexistence of long-range order, a characteristic of solids, and superfluidity. This means that within the same system, some components exhibit rigid, lattice-like structures, while others flow without resistance. The phenomenon arises from the quantum mechanical properties of particles, such as coherence as well as collective interaction. Understanding how supersolidity emerges is going to require a bit of an explanation of how we explore the underlying physics of quantum states, particle wave duality, and the interplay between atomic forces. This makes the field not only challenging, but also incredibly rich for scientific inquiry. The experiment and the findings. The team, led by physicist Antonio Gianfate from CNR, Nanotec, and Davide Nigro at the University of Pavia, conducted meticulous experiments that culminated in this groundbreaking discovery. By manipulating light within specially designed optical systems, the scientists succeeded in orchestrating conditions under which light itself exhibited the supersolid behavior. So let's talk about the experimental setup. The researchers employed an intricate setup involving nonlinear optical materials, which possess properties allowing the light-matter interaction to be finely tuned. Using precisely calibrated lasers, they generated conditions where photons could interact in ways that people had previously thought impossible. But remember, with the divine, all things are possible. So here are some key characteristics of the experimental design. Nonlinear optical media, materials that can change the refractive index in response to intensity of light, enabling complex interactions between photons. Laser configurations, Special arrangements of laser beams were used to create an optical lattice, providing the structured environment necessary for supersolidity. Detection techniques. Advanced photonic sensors were employed to observe and record the behavior of light within the experimental system. This would help ensure the accurate level of data collection needed for this to be a rigorous scientific experiment. Observations. Through the setup, the scientists observed that light behaved in a manner consistent with supersolidity. The photons demonstrated a structured lattice-like arrangement while simultaneously flowing without friction. This hybrid behavior closely paralleled the properties of previously observed atomic supersolids. Notably, the experiment demonstrated that the supersolid behavior of light could be controlled. You do this by adjusting the intensity and the phase of the laser beams. This degree of controllability is a significant advancement. It paves the way for practical applications and deeper experiments in the future exploring this. So what are the implications? Well, first, it advanced quantum physics. This discovery offered a deeper explanation of quantum mechanical properties and the potential for photons to exhibit complex collective behaviors. It challenges the conventional view of light as a simple, non-interacting phenomenon and introduces the possibility of engineered light states with novel properties. The technological innovations. So the practical applications of supersolid light would be far-reaching. Potential areas include the development of highly sensitive sensors, advanced quantum communication systems, and new types of photonic materials. The controlled manipulation of supersolid light might also lead to breakthroughs in optical computing, where light could be used for faster and more efficient data processing. And I think I've talked about that in a video in the past. Fundamental research. Beyond technological implications, the study encourages further exploration of quantum states of matter. It opens the door to researching how other forms of matter and energy could be engineered to exhibit the properties of a supersolid, enhancing our understanding of the fundamental building blocks of our universe around us. So this could lead to new theoretical frameworks. The discovery necessitates the development of refined theoretical models to better explain and better predict the behavior of supersolid light. This could influence various subfields within quantum physics, such as quantum field theory, as well as condensed matter physics. What are our challenges? Well, while this discovery is monumental, it also presents numerous challenges and questions for the future in terms of research. For instance, what about stability and control? Ensuring the stability of supersolid light under varied conditions still is a significant hurdle. It's not an achievement that's easily gotten to. Researchers must develop better methods to sustain this state over longer periods and in diverse environments. Investigations into the effect of external disturbances such as temperature fluctuations and also this electromagnetic interference that can occur is critical. The scaling and integration is important as well. Integrating supersolid light systems into existing technological frameworks poses a challenge from an engineering standpoint. Scientists must determine how to scale these systems for industrial or commercial use without losing the delicate properties that define supersolidity. Keep in mind, this is just not something you can just do every day. What about the theoretical modeling? Current models of light behavior must be expanded to account for these new findings. Science is catching up to the results. This involves complex mathematical simulations and the formulation of new hypotheses regarding the interaction of photons under supersolid conditions. Replicating this experiment again and again. Replication of the experiment in other laboratories will be essential to validate the findings. Remember, science can have some experiment that is somehow talked about, but if other scientists can't replicate the results, they're going to view it as a fluke or perhaps even fabricated. Broader scientific impact. The discovery of supersolid light extends beyond the confines of photonics and quantum physics. It raises philosophical concerns about the nature of reality and the fundamental behaviors of energy and matter. Moreover, it encourages this interdisciplinary collaboration that will be necessary, bridging gaps between physics, material science, and engineering. Researchers across the globe are now poised to explore how this discovery could influence related fields, like cosmology, quantum computing, and even some aspects of biology, where light based technologies could play a very, very pivotal role. In conclusion, the identification of supersolid behavior in light marks a revolutionary moment in physics. I hope you're as excited as I am. As Antonio Gianfate and Davide Nigro aptly stated, this is only the beginning of understanding supersolidity. The implications of this discovery extend beyond academic curiosity. This could be a game changer, potentially reshaping the landscape of quantum mechanics and photonic technologies. As research progresses, the fusion of theoretical insight and practical innovation will undoubtedly reveal more about the mysterious and multifaceted nature of light. This remarkable advancement underscores the ever evolving journey of scientific exploration. This is what it's all about. Being able to find these amazing things and then trying to come up with explanations for it. The endless possibilities arise when curiosity meets ingenuity. The discovery of supersolid light not only enriches our understanding of the quantum world, but it also paves the way for future breakthroughs that could transform science and technologies in ways that we are only just beginning to imagine. With continued exploration and collaboration, the full potential of supersolid light will unfold, offering new insights and applications that promise to redefine our interaction with one of the universe's most fundamental